Hi, everyone. My name is Gabriel.
And I'm Romi.
And we're software engineers at Tesla working on autopilot. We're excited to be here today to talk about how we use Bazel to develop software for cars and robots. But before we get started, I want to play a short video showing you what we've built. That was a video of our full self-driving, or FSD, beta program in action. Now let's look at how it works. The system works by taking in the feed from the 8 cameras around the car and feeding it into the neural networks that recreate the area around the car in 3D, which we call the 3D vector space. We then use a mix of C++ and neural nets for planning and controls. There is a lot of data to process at low latencies, and it's all safety critical. So we had to create our own FSD computer to compute neural net operations faster and more efficiently. We're developing software for this FSD computer, and to make progress quickly, we need 2 things: to be able to iterate quickly on our tech stack and the right infrastructure to support it. This is a simplified diagram of what our workflow looks like. We begin at the top, where we train our neural networks using clips taken from our fleet. We train them on our AI cluster, which we call Dojo, and on our GPU cluster. After training the neural net, we integrate it into the build, evaluate it, and then deploy to our engineering fleet for mileage. And lastly, we deploy to the main fleet in waves. For this talk, we want to focus on build, evaluation, and the FSD computer farm. Starting with the build. I briefly mentioned that our tech stack is a mix of C++ and neural nets. We have many engineers working on the C++ code base, and they need to be able to iterate quickly. To show you how that's done, we'll create a new C++ library. To create a new library, we need to create a new header and source file. We then add includes for the dependencies. And finally, we need to create a CC library target in the build file with the correct depths. From a different perspective, it looks like we're updating the dependency graph twice, once in C++ and again in Bazel. Our goal is to allow engineers to stay focused on the C++ code, and the Bazel targets should be inferred from the source code. So to do that, we use a tool called Gazel. Gazel reads source code and updates or generates the build file. And it can be extended to support any language. So we added support for C++. In order to make full use of the plugin, we've established some best practices. To have a directory managed by the plugin, the build file in the directory has to include our custom directive. We add our directive at the top of the build file and run the tool, and Gazel will give us the build file on the right. Each generated CC library has only one header and one source. And this allows us to make the build more granular, but it has another property too. So the other property is that we have to have the include statement be the full path from the root. What that allows us to do is we can infer what the Bazel dependency is just by reading the include. And it also makes it very easy to figure out what all your dependencies are. And we take the includes from the header, and those become depths. And we take the includes from the source file, and those become implementation depths. So we've looked at C++. Now let's look at neural nets. In the same way that we compile C++ code into a binary that can be run on a machine, we have to compile a neural network into a binary that the car or robot can understand. So we're developing for this FSD computer, which has CPUs, GPUs, and an AI accelerator that we call Trip. Each form of compute is optimized for different workloads. For example, many of our neural net matrix operations run better on the trip. Let's look at an example. This is the occupancy network. As the name implies, it's used to determine whether any given coordinate in the vector space is occupied. And this is what the architecture looks like. Each node is a neural net operation, and the flow is from the top to the bottom. The network is very large, and some of these operations run better on CPU or GPU, while others run better on the trip. So what we have to do is split the network into subgraphs that are optimized for the right compute. The code that does the splitting is a Bazel repository rule that we call partitioner. We started out with a handwritten build file to manage the models, but that became very, very big. And the original partitioner was a custom rule, but it quickly became frustrating to declare each subgraph's dependencies and how the different subgraphs connected to each other. So in the end, we turned the partitioner into a repository rule, and now it loads all the models in the repo, partitions them, and creates each subgraph targeting the right chip. So after splitting the model into subgraphs, each subgraph is compiled using the right compiler. When making changes to a neural net, the main workflow is to update the end nodes, which are shown as the two head nodes on the left. If we change the two head nodes, the head subgraph in the middle will have to be recompiled. But the other subgraphs will all be cache hits. This allows us to iterate very quickly on neural net changes. We've broken up the occupancy network into subgraphs, which can be compiled in parallel, but we also need to look at the long pole. We need to make each subgraph compile quickly. Because we developed the compiler, we were able to split it into 3 steps. Each step is modeled in Bazel using custom rules, and the entire pipeline is implemented as a macro. An engineer can quickly try different strategies, and if the intermediate artifacts are the same, then they can benefit from remote cache hits, and they won't rerun. And this allows the engineers working on the compiler to iterate very quickly. While in this presentation, we've only covered the compiler toolchain for neural networks and C++, we're tackling all parts of the software 2.0 stack. But we'll leave those for next time. And now Romi will talk about how we evaluate our changes.
So we talked about how we build autopilot. Now we'll talk about how we evaluate autopilot performance. We have 2 forms of evaluation. The first form is called open loop evaluation. In open loop, we collect data from a fleet of Tesla vehicles and take this pre-recorded sensor data, feed it into autopilot, and from there record the controls output, verifying whether autopilot performed as expected. The second form of evaluation is called closed loop evaluation. Here, we generate synthetic sensor data via simulation. We feed that into autopilot and record the controls output, same as before. However, because this data is fully synthetic, we can take the controls output and use it to generate new synthetic data in the simulation, closing the loop. Now that we know the 2 types of evaluation, let's see how we can use them to solve issues in autopilot. In this coming video, you'll see a cyclist quickly enter autopilot's lane. In order to avoid the cyclist, autopilot veers left. And you can see on the left here that the car gets very close to vehicles in the left lane. We can see from our data that this was a very uncomfortable experience that we need to address. Autopilot engineers are able to make changes in controls and vision and rerun the simulation. In the rerun, we can see that everything works as expected. Simulation gives us infinite possibilities as we vary the landscape, actors, lighting, and terrain. This gives us a lot of representative power for all our test cases. Now that we understand how open and closed loop simulation helps us on autopilot, let's dive into how Bazel interacts with evaluation and how both run on our servers. We have three components in our data centers: storage, evaluation servers, and FSD computers. Let's dive into each. Our data is comprised of build artifacts stored in our Bazel cache, our Docker images, and data sourced from our customer fleet. This data is fed into our evaluation servers, and here you can clearly see the evaluation loop. The evaluation world state feeds into the renderer. These rendered images and simulated sensors are fed into the autopilot computer. This produces controls output, which is used to update the evaluation world state. From there, we can generate new rendered images for the next cycle. Our data centers run builds and evaluation both on the same machines. Now that we've explored the high-level software architecture, let's look into the hardware that makes this possible. Build and evaluation are demanding tasks that require a large amount of bandwidth and compute. For each build, we move 53 gigs from our Bazel cache, and each simulation requires 45 gigs. These bandwidth requirements present a variety of challenges that we'll talk about later in this presentation. The final simulated images are streamed over a 10 gigabit link per FSD computer. We cover the hardware and software for just one evaluation and one build. Next, we'll cover how we scale both with our FSD computer farm. This is an FSD computer after we add heat sinks, cooling, high-speed networking, and an enclosure. To have this computer fit in a data center, we've grouped them into trays along with fans, relays, power supplies, and heat sensors. Each of these trays are stacked vertically into racks. And we have many rows of these racks in our data center. We have multiple data centers around the world and have over 5,000 computers, FSD computers, and we're growing. In 2018, we had FSD computers running at desk, and our evaluation volume was relatively low. We built our first full rack in 2019 and filled our first data center by the end of 2020 with 30 million simulations of yearly capacity. In 2022, we're running 2 million sims a week, and this kind of scale brings us a lot of unique software challenges across networking, distributed computing, and storage. Given that we're here at BazelCon, let's talk about how this scale impacts our Bazel cache. In the beginning, there were a few machines hitting a single Bazel cache. This cache was implemented as an Nginx server. This simple configuration should be familiar, given it's one of the suggestions on the BazelCon website. As we scaled up, we ran into disk I/O limits as well as space issues on our single cache server. To resolve this, we decided to scale horizontally. We added a load balancer. This solved our disk I/O issues as well as our disk space issues. But with 8 gigabit peak bandwidth per build. Bandwidth into the load balancer became the choke point. We added client-side load balancing and intentionally thought about our data center network topology to eliminate this bottleneck. We used consistent hashing across multiple nodes to ensure that we had cache hits within a single data center. If we zoom out the previous diagram, we get a complete look at a single data center. Ever growing, we expanded to a few more. We wanted to avoid cache misses between data centers and understood that ingress and egress between data centers is a valuable resource. To resolve this, we implemented tiered Bazel caching. Each data center implements write-through and read-through caching. With each new artifact, Bazel writes through the data center local cache and saves it on the master cache in yellow, located in a separate data center. A cache miss inside a data center reads through to the master cache and pulls the artifact from the artifacts into the data center local cache. With this, we ensure high cache hit rates. So Bazel's load is very read heavy, and most reads end within the data center. Because of this, the master cache load remains relatively low and primarily write heavy. So far, this has scaled well for us. Throughout our stack, we record metrics with BuildBuddy and Grafana. We forked BuildBuddy and have been able to instrument it to collect additional metrics. We use the Bazel event service to record how long each target takes and detect regressions. With Grafana, we record high-level infrastructure metrics for our load and aggregate. With all this telemetry, we've recorded our load to be 2 million evaluations, 90,000 builds, 1 petabyte of artifact produced, and 10 million tests every single week. To support this level of load, we had to set up cutting-edge compute across 5 data centers with 1 exaOP of evaluation compute on over 5,000 FSD computers, utilizing over 90,000 cores. These numbers are increasing every few months, and we aren't only scaling our infrastructure, we're also scaling our team. We are hiring, so please check tesla.com/AI if you're interested in joining the team. And thanks, everyone. That's the end of our talk.